Dear students, I am Dr. Ashok Kumar, Saini, Associate Professor in Mathematics in BLJS College, Tosham. Today, I will deliver lecture on real and complex analysis for the class BA BSc third year semester 6th. The textbook that we follow is New College Real and Complex Analysis, Jevonson's publications, and the syllabus for real and complex analysis is this syllabus MDU CBLU Bhiwani is for BA BSc third year 6th semester real and complex analysis section. There are 4 sections. Section 1, Jacobian beta and gamma functions, double and triple integrals, Dirichlet's integral, change of order of integration in double integrals. Section 2, Fourier series, Fourier expansion of piecewise monotonic functions, properties of Fourier coefficients, Dirichlet's conditions, Parseval's identity for Fourier series for even and odd functions, half range series, change of intervals. Section 3, extended complex plane, stereographic projection of complex planes, continuity and differentiability of complex planes, complex functions, analytic functions, Cauchy-Riemann equations, harmonic functions. Now we will discuss about section 3. Section 3, this is Riemann stereographic projection. This is Riemann-Sapir method 1 and this is Riemann-Sapir method 2. Riemann-Sapir method 2. Now we will go at complex functions or functions of a complex variable. If a rule or set of rules be given by means of which it is possible to find one or more value of w equal to u plus iota v for every value of the complex variable z is equal to x plus iota y in a certain domain D, then w is said to be a complex function of z defined on the domain capital D. W is a function of z defined on the domain D, and we write w is equal to function u function of xy plus iota v function of xy equal to fz, where u v are real functions of x and y. So according to this, if a rule or set of rules be given by means of which it is possible to find one or more value of w, one value of w or more value of w is a complex u plus iota v. Iota here is under root is equal to under root minus 1. For every value of the complex variable z equal to x plus iota y in a certain domain D, then x is said to be a complex function of x defined on the domain D, and we write w is equal to u x comma y plus I v x comma y equal to fz, where u comma b are real functions of x and y. If to each value of z there corresponds one and only one value, unique value means of w, then w is said to be a single valued function of z. Otherwise a multi-valued function. For example, w is equal to 1 by z, z is not equal to 0 is a single valued function, and w equal to under root z is a multi-valued function of z. The former is defined at all points of z plane except at z equal to 0, and the latter assumes two values for each value of z except at z equal to 0. To represent w equal to fz graphically, we take two argand diagrams, one to represent point z and the other to represent w. The first diagram is called the z plane. These two diagrams, first diagram is z plane and second diagram is w plane. To represent w equal to fz graphically, we take two argand diagrams, one to represent point z and the other to represent w. The first diagram is called the z plane and the second one is called w plane. This is your z plane and d domain, and w is connected with some rule f, and w equal to fz, x axis y axis. Description for the function w plane and w naught. Remark: if fz equal to z square, then f of x plus iota y z square. Writing z equal to x plus iota y b का whole square, we have x plus iota y whole square equal to x square minus y square plus iota 2xy. We can write this as u plus iota v, where hence uxy here real part is x square minus y square and imaginary part vxy is 2xy. When polar coordinates are used, f r e की power iota theta is equal to r e की power iota theta का whole square equal to r square e की power iota 2 theta is equal to r square cos 2 theta plus iota r square sin 2 theta. Consequently, u r theta is equal to r square cos 2 theta and v r theta equal to r square sin 2 theta. It shows that u and v are functions, and in either equations fz equal to u xy plus iota vxy and fz is equal to u r theta plus iota v r theta. The function b always has value 0, then the value of f is always real. That is, f is a real valued function of a complex variable. Now limit of a complex function. Let w equal to fz be any complex function of z defined in a bounded and closed domain D. We say that fz tends to limit L as z approaches z naught along any path in D if to each positive arbitrary number z epsilon, however small. This definition is similar to limit of a real function. However small, there exists a positive number delta such that absolute value of fz minus L less than epsilon whenever z minus z naught is positive and less than stop for clarity. Stop. whenever theta is z minus z naught less than delta, that is uh, uh, that is this is whenever z minus z naught less than delta and this absolute value is positive. Expanding the absolute value fz, we will get fz in the limit L minus epsilon and L plus epsilon whenever z naught minus delta less than z naught plus delta z is not equal to z naught. We write limit z approach to z naught fz equal to L. Thus above definition means that for any given neighborhood of L there exists a deleted neighborhood of the point z equal to z naught in which absolute value fz minus L can be made as small as we please. This is the figure limit of a complex function. This is z plane and this is z naught, v x axis y axis, and this is z point, this is w plane. Z point correspond to f bracket z and this is L. Fz in w plane, fz approach to L. If there exists an positive number epsilon, however small it may be, we draw a circle with radius epsilon. Here we draw circle with radius delta and z is corresponding to z under rule f in w plane, it becomes fz figure. Note, in the real variable z approach to z naught implies that x approach x naught along the number line either from left or from right. In complex variables z approach to z naught, in real number system x approach to x naught means either we approach x naught from left or from right, whereas in complex variable z approach to z naught implies that z approaches z naught along any path either straight or curved, since the 2 points representing z and z naught in a complex plane can be joined by an infinite number of curves. This is the z to z naught we approach in infinite number of paths. So there is a difference between real limit of a complex function and limit of a real function. We will give an example. Verify by definition that limit z approach to 2 plus 3 iota x plus iota x plus y square equal to 2 plus 11i. Solution, here given z epsilon approach to positive, we have to find delta positive such that absolute value of x plus iota x plus y square minus, this is we have written x plus iota bracket x plus y square minus here x approach to minus L here is 2 plus 11i minus 2 plus 11i. If this is less than epsilon, whenever z approach to 2 plus 3 iota, that is z minus 2 plus 3 iota less than delta, and this is positive. Consider this expression absolute value of x plus iota x plus y square minus 2 plus 11 iota is equal to absolute x minus 2 plus iota x minus 2 plus iota y square minus 9 less than equal to absolute value of x minus 2 plus z minus 2 plus z minus 2 plus we factorize y square minus 9 y minus 3 y plus 3 is equal to 2 z minus 2 plus y minus 3 y plus 3. This is less than epsilon if we assume 2 into z minus 2 absolute value less than epsilon y2 and absolute value y minus 3 y plus 3 is less than epsilon y2. Thus, the first of these is of course satisfied when mod will f x minus 2 less than epsilon y4. To determine the condition on y such that second one holds, we restrict y so that absolute y minus 3 less than 1 and observe that y plus 3 is equal to absolute y minus 3 plus 6 less than equal to absolute y minus 3 plus 0 less than 7. Hence, if y minus 3 less than minimum 1 epsilon y 14, it follows that absolute y minus 3 into y plus 3 absolute value less than epsilon divided by 14 into 7 is equal to epsilon y2. An appropriate value of delta is now easily seen by absolute value x minus 2 less than epsilon y4 and absolute value y minus 3 less than minimum 1 and epsilon y14. Delta equal to minimum, which is minimum either 1 or epsilon y14. We will repeat this problem from here. The first of these is of course satisfied when absolute x minus 2 is less than epsilon y4. This first, this is second, and this is first. If we assume 2 into x minus 2 less than epsilon y2 and this is second, y minus 3 into y plus 3 less than epsilon y2. Now here what he said, this the first of these is of course satisfied when x minus 2 is less than epsilon y4. To determine the condition on y such that second one holds, we restrict y so that y minus 3 absolute value is less than 1 and observe that the second absolute y plus 3, this can be written as y minus 3 plus 6. 3 can be written as minus 3 plus 6, which is by triangle law we have less than equal to y minus 3 plus absolute value 6, and it can be taken as less than 7 because absolute y minus 3 is less than 1. The first factor is less than 1 plus 6 is less than 7. Hence, if y minus 3 absolute value is less than minimum, first is less than 1, y minus 3 is less than 1, and second we have taken epsilon y14. So it follows that hence if y minus 3 less than whichever is smaller, minimum 1, either 1 or epsilon y14, it follows that y minus 3 into y plus 3 less than epsilon y14 into 7. This above is 7 is equal to epsilon y2. An appropriate value of delta is now easily seen by absolute z minus 2 less than epsilon y4 and absolute y minus 3 less than minimum 1 comma epsilon y14. Delta equal to minimum 1 epsilon y14. Now in next chapter we define continuity of a function. Thank you students, and you will see this online lecture on our college website name www.bljscollege.com. If there is any query or any difficulty, you can contact me. Thank you students.